All right, this is question number 2 from the 1999 AP Calculus AB exam. It's an area and volume FRQ, where we're first asked to find the area of region R that is bounded by y equals x squared and y equals 4. So we just need to do an integral of the upper function, which is 4, minus the lower function, which is x squared. And we do need to figure out where they intersect. So just set x squared equal to 4 to get x equals plus or minus 2, right? And we'll just integrate from -2 to 2. Now, this is a calculator question, so you could have your calculator do this for you. But, well, I mean, we might as well. It's a calculator question, right? So we'll just do math option number 9. And we're going to go -2 to 2 of 4 minus x squared. Of course, a very easy integral. Shocking that this was on the calculator section, but you get 10.667. And of course, if you gave the actual exact equivalent to that, which is 32/3, that would be perfectly acceptable as well. And they just gave you 2 points there, 1 for the setup and 1 for the answer. In part B, they want to know the volume of the solid generated by revolving R around the x-axis. So if we go around the x-axis here, we've got washer cross-sections. Right? We have an outer radius equal to the distance from the x-axis to the upper function, which is just going to be 4. And we have an inner radius equal to the distance from the x-axis to the lower function, which is just x squared. And so since these are washers, right there, pi times the outer radius squared minus pi times the inner radius squared is the area of that cross-section. We'll just do pi times the integral from -2 to 2 of our outer radius, 4 squared, minus our inner radius of x squared squared dx. And of course, this is a calculator question again. So you can go ahead and use your calculator for this, although you don't really need to. Don't forget the pi out in front. We'll do math option number 9. And we're going to integrate from -2 to 2. And 4 squared is 16, and x squared squared was x to the 4th dx. And you get 160.850. And of course, if you did this by hand, which you may well have done, you'd end up with 256 pi over 3. Again, either of those answers would be perfectly acceptable on the AP test. And I think nowadays they would not give you a calculator for this. This would really be a non-calculator question more likely. So you should be able to do that by hand. So 3 points here, 1 for the limits and the constant, 1 for the integrand, and 1 for the answer. And in part C, it tells us there exists a number k greater than 4, such that when R is revolved around the line y equals k, the resulting solid has the same volume as the one in part B. And it asks us to write, but not solve, an equation with an integral expression to find k. Well, if it's y equals k up here, once again, we're going to have washer cross sections, but this time, right, we're going to be having an outer radius that is from k down to the lower function. So our outer radius is from k to the lower function, right, this distance. So that's k minus the height of the function x squared. So k minus x squared. And our inner radius is just going to be whatever the value of k is minus 4, right? Because that's just the distance from k to 4, right? K minus 4. And so we'll write this out as pi times the integral from -2 to 2 of our outer radius, k minus x squared, squared, minus our inner radius of k minus 4 squared dx. And we just want this to be equal to our answer from part B, which was 256 pi over, I think I wrote 3 before, but it was 256 pi over 5. So just go back over here and we'll make a note. That was not 256 pi over 3. That was 256 pi over 5. And so that's all you have to do there for part C. Just set it equal to that value. You got 4 points, 1 for the limits and the constant, 2 for the integrand, and 1 for actually setting it equal to your answer from part B. And that's the end of this area and volume FRQ. It was question number 2 from the 1999 AP Calculus AB exam. All right, this is question number 1 from the 2000 AP Calculus AB exam. It's an area and volume FRQ where we're given region R in the first quadrant between y equals e to the negative x squared and y equals 1 minus cosine x. And first we're asked to find the area of region R. And so to find that area, we just need to integrate the upper function, e to the negative x squared, minus the lower function, 1 minus cosine x, from the left bound, which is 0, to the right bound, which is wherever e to the negative x squared equals 1 minus cosine of x. So since this is a calculator question, we'll go to our calculator. We'll hit y equals. We'll graph e to the negative x squared, and we'll graph 1 minus the cosine of x. And we'll graph them both and find that first little intersection point that we were looking at. So second trace, option 5 for intersect. Just go a little closer to that intersection point to the right, hit enter. Scroll a little to the right of the point where it intersects, hit enter, and hit enter once more to get they intersect at 0.941941. So we'll make a note that that's 0.941941. And I'm just going to call that A so that I don't have to keep rewriting that. And we're just going to put an A here. And then we'll use our calculator to find that integral. And one thing we can do is we can go over here and just type that number, 0.941941, in and hit STO with the arrow just above the on button. And then hit alpha and math, which is alpha A. And now that number is stored as A. So when I do my integral by hitting math 9, I don't have to keep retyping that value and have a chance of messing it up. I can just hit alpha A. And we're doing our upper function, which was e to the negative x squared, minus our lower function of 1 minus cosine x. So it'll be e to the negative x squared minus the quantity 1 minus cosine x. Don't forget the parentheses around the 1 minus cosine x. And then your dx, and then you get 0.591 when you round. And they gave you 2 points, 1 for the integrand and 1 for the answer. But they also gave you 1 point if you had the correct limits anywhere in parts A, B, or C. So we've earned that point here. We've now got 3 of our 9 points here for this FRQ. In part B, it wants us to find the volume of a solid generated when region R is revolved about the x-axis. And so this is just a standard washer cross-section problem, right? We have an outer and an inner radius. I guess I definitely drew that second one way too big on the bottom, but that's fine. Yeah, an outer and an inner radius. And our outer radius just extends from what we're revolving around, which is the x-axis, up to the upper function right up here, which is a y value of e to the negative x squared. And our inner radius just extends from the x-axis up to the other function. And so the area of that cross-section is just pi times the outer radius squared minus pi times the inner radius squared. So we'll just integrate, and it'll be pi times that integral from 0 to a of the outer radius, e to the negative x squared, minus the inner radius of 1 minus cosine x squared dx. And again, we'll just use our calculator to find this value. Now, when we do this, we can just put our pi out in front. Don't forget the pi. And then math option 9 for our integral from 0 still to just a. And then just to make sure you don't make an error with the e to the negative x squared and the 1 minus cosine x squared, we can use this little trick that we already have e to the negative x squared graphed as our y1 and 1 minus cosine x as our y2. So you can hit the VARS button for variables just next to clear. Go over to the second column, option 1, and it'll just give you a drop-down menu of all your functions. So we'll just choose option 1 for y1, and then we'll square it. And then we'll subtract and do the same thing. Variables, VARS, the second column, and number 2. And then we'll square that one. And then there's no chance of typing it in wrong, messing up the parentheses or anything like that. And you just hit enter and get 1.747 when you're round. And that's worth 3 points, 2 for the integrand and the constants and everything over there, and 1 for the final answer. And in part C, it says region R is the base of a solid, and the cross sections perpendicular to the x-axis are squares. Find the volume. Well, it's just a volume by cross sections again. Right, so the area of this cross section is just the side length squared, where the side length is the upper function minus the lower function. So we're just going to integrate from 0 to a of e to the negative x squared minus 1 minus cosine x, all squared, since it's the side length squared. And again, we'll just use our calculator. We're going to do math option number 9, and you can just hit the 9. You don't have to scroll all the way down. We're going to integrate from 0 to a, right, alpha and the math button. And we're going to use that same trick. We'll just do y1 minus y2 squared. I'm going to put it in parentheses. Y1, so VARS, second column, option 1, and then minus, and then the same thing, VARS to get that other function, second column, and option number 2 down there. Close your parentheses and square it. Put your dx, and you end up getting 0.461. And that was worth 3 points yet again. 2 for the entire integrand and 1 for the answer. And that's the end of this area and volume FRQs, question number 1 from the 2000 AP Calculus AB exam. All right, this is question number 1 from the 2001 AP Calculus AB exam. It's an area and volume FRQ. And we're given 2 regions, R and S. In the first quadrant, R is bounded by the x-axis and 2 minus x cubed in tangent x. And S is the y-axis, and they same 2 functions. And so first we want to find the area of R. So in order to find the area of R, we're going to need to figure out where these 2 functions intersect. Right? When does tangent x equal 2 minus x cubed? Because in order to do that, right, we have to, in order to find that area, we have to split that into 2 regions, because the upper bound of the region changes from tangent x to 2 minus x cubed at that point. So we'll go into our graphing calculator. We'll graph tangent x. And we'll graph 2 minus x cubed. And we'll just see where they intersect. And so we'll do second trace. Option number 5 for intersect. And we'll come up kind of close to where they intersect, hit enter, go a little past where they intersect, hit enter, and hit enter again, and we get an x value of 0.902155. And just in case we need it, maybe we'll note down the y value. The y value there was 1.2657507. And we might need that in a later part, so good to just jot it down. So to find the area of R, and I'm going to call this A, and I'll call this B, just so I don't have to keep rewriting them. We're just going to integrate from 0 to A of our tangent function. And we'll add to it the integral from A to wherever the 2 minus x cubed function intersects the x-axis. And you can get a decimal approximation for that, or you can just solve this and get x equals the cube root of 2. Either way is fine. Of our 2 minus x cubed dx. And then another option would have been to do the rightmost function minus the leftmost function, right? So we could have done the 2 minus x cubed minus the tangent x, where we put x into terms of y, right? And so then this other one would have been x equals the cube root of 2 minus y. So we could have done cube root of 2 minus y minus inverse tangent y from 0 to that b value. But you don't need to do them both. We'll just do this one. We're going to go out of here. We're going to hit math and go down to option number 9 and do an integral from 0 to that a value, which was 0.902155. And at first, our first function that bounded it was tangent x. And then we will then integrate from that same value, 0.902155, up to the cube root of 2. We can get the cube root of 2 by hitting math and down to option number 4 for cube root. So the cube root of 2 of our other function, which was 2 minus x to the third power dx. And looks like when we add those together, we get 0.729. And they gave you 3 points there. 1 for the limits and the integrands, and then for the final answer. In part B, they want us to find the area of S. Now, the area of S, we're looking at the upper function is tangent x, and the lower function is 2 minus x cubed. So we're just going to integrate that from 0 to, and I just wrote those backwards. That's not our upper function. Our upper function is 2 minus x cubed. So it's 2 minus x cubed minus tangent x. And we're going to integrate that from 0, the left bound, to that a value that was our right bound, which was, that 0.9 value. So that's all we have to do to find that area. We'll just go into our graphing calculator. We're going to do math option number 9. We're going to integrate from 0 to that a value, which is 0.902155. And as we said, it was our upper function, 2 minus x to the third minus the tangent of x dx. And it looks like we get 1.161 when we round. And that was worth another 3 points, 1 for the correct limits, 1 for the correct integrand, and 1 for the final answer. And in part C, it says find the volume of the solid if we revolve S around the x-axis. So if we go around the x-axis here, we're going to have washer cross-sections. We're going to have an outer radius and an inner radius. And our outer radius is just going to be our upper function, which was 2 minus x cubed. And our inner radius is just the distance from the x-axis to the other function, which was tangent. And so now we'll just do the cross sections are pi times the outer radius squared minus the inner radius squared. So it'll be pi times the integral from 0 to a of our outer radius, 2 minus x cubed squared minus tangent squared. And we'll just use our calculator to evaluate that. And we'll note, because we're going to have to square these, it might be nice. If we look in here, we had tangent as our y1 and 2 minus x cubed is our y2. So when we do this, we're going to do pi. Don't forget the pi out in front. And math, option number 9 for our integral from 0 to a again. But we want to do 2 minus x cubed squared. And 2 minus x cubed, as we just saw, right, was our y2 function. So we can hit the VARS button, which is right next to clear. Go over to the second column, pick function, and 2 minus x cubed is y2. So we can just do y2 squared. And then minus, we can do the same thing, VARS, second column, option 1. And it's number 1. y1 was our tangent function squared. dx. Don't have to retype the functions, and you just get 8.332. And that's our final answer. We got 3 points there, 1 for the limits and the constant, 1 for the integrand, and 1 for the final answer. And that's the end of this area and volume FRQs, question number 1 from the 2001 AP Calculus AB exam. All right, this is question number 1 from the 2002 AP Calculus AB exam. It's an area and volume FRQ, where we're given 2 functions, f, which is e to the x, and g, which is ln of x. And we want to find the area of the region enclosed by the graphs between 1/2 and 1. So if you're not sure which one is above the other one, you should be, but if you're not, just go ahead and go to your graphing calculator and graph the 2 functions, right? So we'll graph e to the x, and we'll graph ln of x. And we're talking about on the interval from 1/2 to 1. So maybe we'll just make our window like 0 to 2, just so we can see it a little bit more closely up here. Our first one that we graphed was e to the x, right? And we can see that that one's above ln of x, right? So what we want to do is we just want to graph from 1/2 to 1, e to the x minus the ln of x dx. And we are allowed to use our calculator here, so we might as well just use our calculator. We'll go back to our graphing calculator. We'll go out of there. We'll hit math. Go down to option 9. You can just hit number 9. We're going to go from 1/2, which is 0.5, to 1 of e to the x minus the natural log of x dx. And we just get 1.223. And they gave you 2 points there, 1 for the setup and 1 for the answer. In part B, it says we want the volume of the solid generated if we revolve that region around the line y equals 4. So we're looking at ln of x and e to the x, and we want to go around the line y equals 4. So if we're going to do that, right, we're taking this region, let's say right here. Well, that's not great. Let's say it's this region, because the ln of 1 is 0, so should probably make it look a little more accurate. When we do that, we're going to revolve around, we're going to get these washer cross sections, right? Where our outer radius is going to extend from the line y equals 4 down to that bottom function, right? So we're going to do 4 minus ln of x. And our inner radius is going to be 4 minus e to the x, right? Because the whole distance here is 4. If I subtract the values of ln x, that's actually like adding some extra to that, right? Because it's below the x-axis. So that's going to get that little extra bit that's below the x-axis. And if I subtract the values of e to x, that's going to take off that little portion between e to the x and the x-axis. So we have pi times our outer radius squared minus our inner radius squared, integrated from 1/2 to 1. And so we'll just put that into our graphing calculator. Don't forget your pi out in front. We'll hit math, option number 9. And we have from 1/2 to 1. And then inside of a new parenthesis, we're going to say 4 minus the natural log of x squared minus 4 minus e to the x squared dx. And it looks like we get 23.609. And they gave you 4 points for that. They gave you 1 point for the limits and the constant, 2 points for the integrand, and 1 point for the final answer. And here in part C, we're given a new function, h, which is f minus g. We want to find the absolute minimum of h on the interval from 1/2 to 1 and the absolute maximum on that same closed interval. So if h is f minus g, right, h of x is f minus g, then h prime of x should just be the derivative of that, which is the derivative of e to the x is e to the x, and the derivative of natural log of x is 1 over x. So first we need to see when on the interval from 1/2 to 1 is e to the x minus 1 over x equal to 0. So we'll go back into our graphing calculator and we'll just type in the function e to the x minus, and I'm going to hit alpha x here to make a nice little fraction, 1 over x. And we'll see when it's equal to 0. It looks like, we have the window 0 to 2. It looks like we have one place there between 0 and 1 where it is. So we'll see if that's on the interval 1/2 to 1. We'll hit second trace. We'll go down to option 2 for 0. We'll scroll till we're a little to the left there of that intersection point with the x-axis. Hit enter. Go a little to the right. Hit enter. Hit enter a third time, and we get x is 0.5671433. And then if we take a little bit of time here to do some analysis, we know that we also need to check the endpoints, right? And so those are x equals 1/2 and x equals 1. But if we look here, we know that our derivative is negative, and then it's positive, right? So our function is decreasing, and then our function is increasing. So we know that this is actually going to be where our minimum is. But our maximum could be at either 1/2 or at 1. And so I think it's, just looking at the graph, we could probably tell that it's going to be at 1 because there's a lot more area there after that intersection point with the x-axis, but that's okay. We still just need to find h of 1/2, h of 0.5671433, and h of 1. And h of 1, right, should be pretty straightforward. H of 1 is just e to the first minus the natural log of 1, which is 0. So h of 1 is just e, which we know is about 2.718. And then now we'll just find h of 1/2 and h of 0.5671433. So we have h prime graph, so we can't use the graph to do it. We'll just do it right here. H was, as we said, equal to f minus g, or e to the x minus ln of x. So we're going to do e to the 0.5 minus the ln of 0.5, which gives us 2.342 if we round. And then we'll do the same for 0.5671433. We'll do e to the 0.567, 5671433 minus the natural log of 0.5671433, which gives us 2.330. And so we can see that that one is the absolute minimum. And that e, h of 1 equal to e, was our absolute maximum. And they gave you 3 points for that. They gave you 1 point just for setting h prime equal to 0, 1 point for identifying the critical point of the endpoints as candidates, and 1 point for the final answer. And that's the end of this area and volume FRQs question number 1 from the 2002 AP Calculus AB exam. All right, this is question number 1 from the 2002 Form B AP Calculus AB exam. It's an area and volume FRQ where we're given region R bounded by the y-axis, x cubed over 1 plus x squared, and 4 minus 2x. And it just asks us to find the area of R. So we're just going to integrate the upper function minus the lower function. So that's going to be 4 minus 2x minus x cubed over 1 plus x squared. And we're going to do it from the y-axis, which is x equals 0, to whatever this intersection point is. So we'll need to find that intersection point. So since this is a calculator question, we'll just use our calculator to see when 4 minus 2x equals x cubed over 1 plus x squared. And you need to write that out since you're having your calculator evaluate it. And we'll go in and we'll graph it. So our first function was 4 minus 2x. And our second function, I'm going to hit alpha x to get this nice fraction bar. And then it's x to the third over 1 plus x squared. And we're just going to graph these. And we can see that they've got that nice little intersection point there. We're going to hit second trace, option number 5 for intersect. And just kind of go over close to that intersection point and hit enter. Go a little to the right of it, hit enter again, and hit enter a third time, and we get 1.4876644. So we'll note that value. It was 1.4876644. And I'm going to just call that A, so that I don't have to keep rewriting that here. So we're going to integrate from 0 to A of our upper function minus our lower function. And so we'll go back to our graphing calculator here. And I have a feeling we're going to need to use that A value again. So what I'm going to do is I'm going to just type that number 1.4876644 once, and I'm going to hit STO with the arrow and store it as alpha, and then the math button, which is A. And now I can just type in A each time instead of having to retype that whole number. So now we want the integral. So math, option number 9. We're going to integrate from 0 to A, alpha A. Right? And we've already typed in our functions. Our upper function was 4 minus 2x. That was in the y1 column here, right, in our y equals screen. And y2 was x cubed over 1 plus x squared. And so what we'll do is we're going to hit the VARS button, which is right next to the clear. Go over to the second column, and in function, we can just see our y1 and our y2. So we'll just type y1 minus, and we'll do the same thing, VARS in that second column again, option 2 for y2. We'll throw our dx out, and we don't have to retype those functions, and we get 3.215. And they gave you 2 points here, 1 for the correct integrand, 1 for the correct answer. And then if you had the correct limits in any of the integrals that you have in A, B, and C, so we did have one here, they gave you a third point. In part B, it asks us to find the volume of the solid generated when R is revolved around the x-axis. So if we're going to revolve around the x-axis, we're going to get these washer cross sections, right? Where we have an outer radius and our inner radius. And our outer radius is just going to be the upper function, right? 4 minus 2x squared. And our inner radius is just going to be the lower function, right? It's going to be x cubed over 1 plus x squared. And so the cross-sectional area is going to be pi times the outer radius squared minus the inner radius squared, right? And I don't know why I wrote the squareds on there, right? Our radius is just the function itself, right? When we do the pi r squared, we have, that's when we square it. So we're going to integrate pi times we're going to do 0 to a of our outer radius squared. So 4 minus 2x squared minus our inner radius, x cubed over 1 plus x squared dx. And it's pretty standard washer solid of revolution problem. And we're just going to use our graphing calculator to find this value. We'll put our pi out in front. Don't forget the pi. Big common mistake to just lose 1 point accidentally with forgetting the pi. We'll do math option number 9. we're going to again integrate from 0 to a. And we can use that same trick, VARS, in the second column to get y1. And we'll square it. And then we'll subtract, same thing, VARS, second column. And we want option 2, y2. And we'll square that. We'll throw our dx out at the end. And we get 31.885. And they gave you 3 points for that, 2 for the integrands and the constants and all that, and 1 for the correct answer from your calculator. And in part C, we've got region R is the base of a solid, and the cross sections perpendicular to the x-axis are squares. Find the volume. Well, if the cross sections are squares, the area of those is the side length squared, and the side length is just the upper function minus the lower function. So we're just going to integrate from 0 to a, our upper minus our lower squared, because it's the side length squared. And again, we'll just have our calculator do this. So we're going to do math option number 9. You can just hit the 9. You don't have to scroll down. We're going to integrate 0 to a, and it's the upper minus the lower squared. So I'm going to put a parenthesis, and I'll use that VARS again. It's just upper y1 minus VARS in that second column to give us y2. And then we will square that with our dx. And we end up getting 8.997. And that's our final answer there. They gave you 3 points, 2 for the correct integrand and 1 for the correct answer. And that's the end of this area and volume FRQs, question number 1 from the 2002 Form B AP Calculus AB exam. All right, this is question number 1 from the 2003 AP Calculus AB exam. It's an area and volume FRQ, and it's a calculator question. And we're given region R that is bounded by root x and e to the negative 3x, as well as the vertical line x equals 1. And we want to find the area of R. So first we need to note that the upper function here, we should be able to tell that's root x. And the lower function here, right, that's e to the negative 3x. And so all we want to do is just find the area. So we just want to integrate the upper function minus the lower function on the interval that's bounding this region, right? And so we know that the end of this is at 1, but we do need to find that first intersection point there. And so we'll note off to the side that e to the negative 3x is equal to root x. And we'll go into our graphing calculator. We'll graph the two functions. So I'm just going to put in square root of x, and I'm going to put in e to the negative 3x. And when I graph them, I should be able to find that intersection point. Right, I'm going to zoom in just a little bit here, right around the origin, so I can see a little bit better. Just hit zoom and then zoom in and hit enter. And then I'm going to hit second, trace, and pick intersect to find where the two functions intersect, option 5. And I'm just going to go over close to that intersection point and hit enter. Go a little past it, hit enter, and hit enter a third time. And see that that intersection point is 0.238731. That's the x value, right? So I'm going to say x equals 0.238734 1, I think it was. Yeah. And then I'm just going to note the y value also, just in case I need it somewhere along the line here. So I'm just going to say y is 0.488603, right? 0.488603 there. And so now all we want to do is just integrate from a, as I've now called this, right? I'm going to call this value a. I'm going to call the other one b. We're just going to integrate from a to 1 of the upper minus the lower. So we'll go back to our graph. We'll hit second, quit. We're going to hit math, option number 9 for an integral. And we're going to go from that a value, which we just said was 0.23873341, up to 1. of the upper function, which we knew was root x, minus our lower function, which was e to the negative 3x dx. And we end up getting 0.443 when we round. And they gave you 3 points here. One just for having the correct limits. That point could have been gotten in parts B or C. Just having the correct limits in any of the parts would have got you that point. 1 point for the integrand and 1 point for the answer. All right, in part B, we're going to find the volume of this solid if we revolve it around y equals 1, right? So if we revolve around y equals 1, we can see that the region here that we're talking about, region R, is not fully pushed up against that axis, which means that we have washer cross sections here, right? Which means we're going to have an outer radius and an inner radius. And we're going to have these washers, like a circle with a circle cut out of them. And our outer radius is going to extend from 1 to the lower function, and our inner radius is going to extend from 1 to the upper function. So our outer radius is just the entire distance of 1 minus that bottom function. So 1 minus e to the negative 3x. And our inner function is going to be 1 minus the upper function, right? This function, which is just root x. And the format here is pi times the outer radius squared minus the inner radius squared integrated across that region, which is from a to 1 once again. So it's our outer radius, 1 minus e to the negative 3x squared, and then minus 1 minus root x squared dx. And we'll just go ahead and put this into our graphing calculator again. Don't forget your pi out in the front. It's math option number 9. And we're going to go from the same value, 0.2387341, up to 1. And now it is 1 minus, we'll put this in parentheses, 1 minus e to the negative 3x squared, and then minus 1 minus root x squared dx. And we end up getting 1.424 when we round. And that was worth 3 points, 2 for the correct integrand, and 1 for the final answer. Here in part C, we're looking now at the region being the base of a solid, and each cross section, perpendicular to the x-axis, is a rectangle whose height is 5 times the length of its base, which stretches across region R. So here's the base, and coming out of the screen, right, is the height, which is 5 times the base. So the area of each of those cross sections is just b times 5b, or 5b squared, where b is just the distance across that region, right? B is just the upper function minus the lower function. And so all we have to do is sum together the infinite number of those little cross sections across A to 1. So it'll be 5 times root x minus 3e to the negative x squared dx. And so we just have to put that into our graphing calculator. We'll do math option 9. And we're going to go from 0.2387341 up to 1. And we have 5 times our root x, our upper function, minus our 3e to the negative x, our lower function. And then we're squaring just the root x minus 3e to the negative x portion of it. Put your dx out there, and you end up getting that's not the right value, so we must have typed something in wrong there. Oh, I put in 3e to the negative x, not e to the negative 3x. So let's go back and fix that. You can just go up and highlight it. We'll get rid of that 3, and we'll insert our 3 up there, and now we should get the right answer, which is 1.555. 4. And that is the end of this area and volume question. You got 2 points here for the integrand, 1 for the answer. 3 total points in part C, and that's the end of the area and volume FRQ. Question number 1 from the 2003 AP Calculus AB exam. All right, this is question number 1 from the 2003 Form B AP Calculus AB exam. It's a calculator question. That's an area and volume question. And we're given a function f of x, 4x squared minus x cubed, and a line, 18 minus 3x, where L is tangent to the graph of f. And then we have 2 regions, region R and region S. Right? We can see region R is just the region between f of x and the x-axis over there in the first quadrant, and S is the region between the graph of f and the line in the x-axis. And we want to show that L is tangent to the graph of y equals f of x at the point where x equals 3. Well, in order to show that, we just need to show what the derivative of f is, and that f of 3 is equal to the correct value for that line so that they match up at the right point. So first we'll find f of 3. Right? F of 3 is just 4 times 3 squared. That's 4 times 9, right? 36 minus 3 cubed, right? Which is 27. And so f of 3 is just 9. I'm not sure how I wrote a 9 that looks like that, but f of 3 is just 9. And then we also need f prime of 3. So f prime of x is just going to be 8x minus 3x squared, taking the derivative. So f prime of 3 is just going to be 24 minus 27, which is negative 3. And so we just write this in point-slope form to start. Y minus our y value of 9 equals negative 3 times x minus our x value, which was 3. We get y minus 9 equals negative 3x plus 9. Add another 9, and you get y equals 9, and 9 is 18 minus the 3x. And so we can see that that is the line that we were talking about. They gave you 2 points there. Okay? 1 for finding f prime of 3, and 1 for finding f of 3, and another one for finding that tangent line. Right? So that's part A, 2 points there. In part B, it wants us to find the area of region S. And so to find the area of region S, we're going to need to break this into 2 pieces, right? Because up until this x-intercept, the upper function is the line and the lower function is f of x. But after that, we just have this triangular piece where only the line is above the x-axis. It doesn't matter what f of x is anymore. That's not our lower bound. So we need to figure out, when does 4x squared minus x cubed hit the x-axis? Now, this is a calculator question, so if you don't feel like doing this by hand, you don't need to. But we'll do that. We'll do it by hand anyway. So like, just factor out the x squared, right? And you get 4 minus x. So you get that x is 0 and x is 4. I think that's quicker than even bothering to graph it and solve it. And we know that this intersection point up here is 3. So we need the integral from 3 to 4 of the line, 18 minus 3x, minus f of x, which is 4x squared minus x cubed, to start with. And then we need to add to that the area underneath that line, which we could just do an integral from 4 to this intersection point, which, well, we need to figure that out too. When does that equal 0? Looks like that's when x is 6. Right? So we could just do the integral of the line from 4 to 6, or we could just say, well, it's a triangle. It's got a base of 2, and at x equals 4, right, 18 minus 3 times 4 is 18 minus 12, which is also 6. So we could just put in a 6 here as our height. And so we could see then that we're just going to evaluate this integral, and that should give us our value. So we'll use our calculator to do this. we're going to do math, and we're going to do option number 9. We wanted the integral from 3 to 4 of 18 minus 3x. And then we're going to subtract the other function, which was 4x squared minus x to the third. And we've got our dx out there. And then we're adding to it, it was 1/2 of 2 times 6, which is just 6. And so when we do that, it looks like we get 7.917. And they give you 4 points for that. They gave you 1 point for finding the integral here of the, or actually 2 points for the integral of the non-triangular region portion, 1 for the area of the triangular region, and 1 for the final answer. And of course, what you could have done also is you could have found the area of the entire triangle, right? And then just subtracted off this piece that is below the curve. So we could have found the bigger triangle, 1/2 of the triangle that's got a base of 3 and a height of 9, and we could have subtracted off just the area underneath f of x from 3 to 4, and either of those would have worked. Here in part C, we want to find the volume of the solid generated if we revolve R around the x-axis. Well, if we revolve R around the x-axis, right, we're just getting disk cross sections here because that region is fully pushed up against the x-axis, right? And so when we do disk cross sections, it's just pi times the integral across the region of the radius squared, which in this case, our radius is just the distance from the function down to the x-axis, right? So it's just f of x squared dx. And we're integrating across the whole region, so we're starting at 0, and then that location where we ended up hitting the x-axis, as we said a minute ago, was 4. So all we need is the integral from 0 to 4 of f of x squared times pi, and we'll use our calculator to do that. Don't forget the pi out in front. A lot of people forget the pi out in front. We want math option number 9 for our integral. We're going to go from 0 to 4. And inside of here, we just have our function, which was 4x squared minus x to the third. And then we're going to square it for that radius squared. With our dx gives us 490.208. And they gave you 3 points for that part. 1 point for the pi and the 0 to 4, 1 point for the correct integrand, and 1 point for the final answer. And that is the end of this area and volume FRQ question number 1 from the 2003 Form B AP Calculus AB exam. All right, this is question number 2 from the 2004 AP Calculus AB exam. It's an area and volume FRQ. We're given 2 functions here, f and g. Right, f of x is 2x times 1 minus x, and g of x is 3 times x minus 1 times root x. And they've given us the region here between the 2 functions, and it even indicated which ones are f and g, and it just wants us to find the area. So we can see that they intersect at 0 and 1. So all we need to do to find the area is just integrate from 0 to 1 the upper function minus the lower function, which is just f of x minus g of x. And since this is a calculator question, we can just use our calculator to do this. So we will. We'll just hit math and go down to option number 9, FNINT. And we're going to integrate from 0 to 1. And it'll be the upper function, which was f of x. So that was 2x times 1 minus x. And then we'll subtract from that the lower function, which I'll put in parentheses. It was 3 times x minus 1 times the square root of x. And then we'll just put our dx out there at the end. And looks like we get 1.133. And they gave you 2 points for that, 1 for the correct integral setup and 1 for the correct final answer. In part B,
we are looking for the volume of the solid generated when the region is revolved around the horizontal line y equals 2, which is clearly up above the region, right? And that region is not fully pushed up against that axis, which means when we revolve around that line, we end up getting these washer cross sections, right? And these washer cross sections, they look like a circle with a circle cut out of the middle of them, right? They have pi times the outer radius squared minus pi times the inner radius squared as their area. And so we just need to figure out what the outer radius and the inner radius each are, right? And we know that this distance here is 2. And so in order to get the outer and the inner radius, well, the outer radius extends from 2 all the way down to this lower function, right? So that's 2 minus the value of g of x, because all the values of g of x are negative. So if I subtract the values of g of x, that should give us a number larger than 2, right? So this is our outer, is 2 minus g of x. And our inner is just going to be 2 minus f of x. Right? So all we do is pi times the integral from 0 to 1 of the outer radius squared, so 2 minus g of x squared, and then minus 2 minus f of x squared dx. And of course, we're just going to put that into our calculator and get an answer. Don't forget the pi out in the front. We've got math option 9, an integral from 0 to 1. And our first radius is 2 minus g of x. So that's 2 minus 3 times x minus 1 times the square root of x. And then we're going to square that. And then we're going to subtract our inner radius, which we'll need a new parentheses here for. That'll be 2 minus, and then it's going to be the other function, right, which was 2x times 1 minus x. And we'll also square that. Throw your dx out at the end, and you end up getting 16.179. And we got 4 points there for that. 1 for the limits and the constant, 2 for the integrand, and 1 for the final answer. And here in part C, it says we've got a new function, h, that is given by kx times 1 minus x. And we've got x between 0 and 1, so the same kind of bounds we have in this first one. And for every k greater than 0, the region enclosed between h and g is the base of a solid with square cross sections perpendicular to the x-axis. And so what we want to do, we're saying there's a value of k for which this volume is 15. We want to write but not solve an equation with an integral that could be used to find k. This is essentially going, if we have something like kx times 1 minus x, it's essentially going to just look like f of x, right? It's just going to depend on how high that goes up. So we know that that function, kx times 1 minus x, is always going to be positive on 0 to 1, right? Because if I put in something between 0 and 1 to this, that's greater than 0. And k greater than 0 and x on 0 to 1 indicates that this is also greater than 0. So we know we're going to have something above the x-axis there, which means that it's going to be the upper function, right? H of x will be the upper function. And so if the cross sections are squares, right, projecting out of the screen towards you, well, we know that the area of those squares is just the side length squared. And the side length will just be, if we're pretending that's h of x now, right, the side length will just be h of x minus g of x, the upper function minus the lower function. So all we really need to do is we need to integrate from 0 to 1 our function h of x, so kx times 1 minus x, and then minus our g of x function, which is 3 times x minus 1 root x, and then square it because that's what gives us the area. And I'm writing it out because it wanted there to be, it wanted us to have an expression to find k, so I'm making sure that we've at least written the k. You could probably write h minus g and then square it in there. h of x minus g of x squared inside the integral will be fine. And then what we have to do is we have to set it equal to the volume that it says it wants it to be, because that just finds us the volume. So this should be equal to 15. If we were able to solve this integral, that would give us the value of k that makes that 15. That's worth 3 points, 2 points for the correct integrand, and 1 point for having the whole thing together with the equals 15 to get your final answer. And that is the end of this area and volume FRQ. It was question number 2 from the 2004 AP Calculus AB exam. All right, this is question number 1 from the 2004 Form B AP Calculus AB exam, where it's an area and volume FRQ. And it says R is the region between the graph of y equals root x minus 1, the x-axis, and the line x equals 10. And so, I mean, we know what root x minus 1 looks like, right? It's just been shifted to the right one. Right here's x equals 10. And of course, this is, if we plug in that, we get, this is the point 10, comma 3. Right? And so we're talking about this region right here that we're looking for the area of. Now, it's a calculator question, so we could have our calculator do this integral, right? And we know this is 1, right, where we're intersecting the x, or touching the x-axis there. So we could use our calculator to integrate from 1 to 10 root x minus 1 dx. Of course, we could do that, but it's easy enough to do it without a calculator. I think probably good practice. If you want to just punch it into your calculator, go ahead. If it was the AP test, go ahead and do it, right? Because, you know, you might make an arithmetic error. But we know that when we do the u sub for x minus 1 here, du is just dx. And so really, it's just like doing u to the 1/2, right? So it just ends up being 2/3 of x minus 1 to the 3/2. It's one of those easy ones where you don't really have to worry about the u sub, because the u is x plus or minus some constant, right? X plus or minus a. And so now we're just going to plug in our value. So we have 2/3 of 10 minus 1 is 9, and 9 to the 3/2, you square root the 9 first to get 3, and then cube it to get 27. And then we'll subtract what we get when we plug in 1, which is just 0. Right? And so what we end up with there is 2/3 of 27, which is just 18. And of course, you could have got that on your calculator, but easy enough to do it this way as well, and good practice for us in general. So 1 for the correct limits, 1 for the correct integrand, and 1 for the final answer. No points for the actual antiderivative because it was a calculator question and you could have just done it on your calculator. In part B, it says, find the volume of the solid generated if we revolve this around the line y equals 3. So let me resketch this picture here. And if we're going to go around y equals 3, we already established that this point here was the point 10, comma 3. So we're going around that line, and we're taking, I should move my y-axis over here just a bit, right? Because we know that we're hitting here at 1, right? So we're going around this horizontal line of y equals 3, and since the region that we're talking about right here is not fully pushed up against that line, we end up with washer cross sections, right? We end up with these washers as we go along here that have a thickness of dx. Right? And the outer radius extends from the lower bound of the region all the way up to the line y equals 3. So our outer radius of that washer is going to just be 3. The inner radius extends from the line y equals 3 to the upper bound of the function. So my inner radius is actually the entire distance of 3 minus this distance from the x-axis to the function. So 3 minus root x minus 1. And so now, in order to find the value of the volume, we have to use our method for washer cross sections, because the area of the washer is pi times the outer radius squared minus the inner radius squared, right, where the pi is being multiplied to both of them. So it's pi times the integral from 1 to 10, same limits as the first part, of the outer radius squared minus the inner radius squared dx. And so now this time we will just use our calculator to evaluate this. So we'll go to our graphing calculator. Don't forget to put your pi out in front. That's a pretty common mistake. then hit math, option number 9. We're going to integrate from 1 to 10, and it's 3 squared was our first part, so 9, minus, and then I'm going to put my second radius in parentheses here. It was 3 minus the square root of x minus 1, and that needs to be squared with a dx out at the end. And so we integrate that and get 212.058 when we round. And part B here was also worth 3 points, 1 for the limits and the constant, 1 for the correct integrand, and 1 for the final answer. In part C, it says, what's the volume of the solid generated when R is revolved about the vertical line x equals 10? So now we have this same region here, right? Here's x equals 10, but now we're going to revolve it around x equals 10, giving us disk cross sections that, the radius extends from the function over to the line x equals 10, right? And they're disks, not washers, because that region is fully pushed up against the line that we're revolving around, right? X equals 10 is one of the bounds of our region. So all we have to do is pi times an integral of the radius squared, but note that the thickness of these is in the y direction, dy. So we're going to have to do this integral in terms of y, which means when we integrate, we're going to integrate from the bottom of the region, 0, to the top of the region, which was 3, rather than from 1 to 10 like we did in the last couple of integrals. And so now we just need to figure out, what is this radius? Well, we'll note that the distance from the y-axis to the function is always x. And this entire distance is 10. So our radius here should be 10 minus x. But I can't just put 10 minus x and squared inside of here, because we have to integrate in terms of y. So we have to figure out what x is in terms of y. So if y is equal to root x minus 1, square both sides to get y squared equals x minus 1, and then x is equal to 1 plus y squared. And so now we can put this in here that our radius is 10 minus the quantity 1 plus y squared, and we want to square that radius and then integrate. So we'll go ahead and we will put that into our graphing calculators. We'll put our pi out in front. We'll do math option number 9. And again, you can just hit 9. You don't have to scroll down to it. We're going to integrate from 0 to 3. And our radius here, which I'm going to put in its own set of parentheses, is 10 minus the quantity 1 plus y squared. We're just going to use x squared here. Close the parenthesis on the 1 plus x squared and the 10 minus 1 plus x squared. Now that we have our whole radius in parentheses, we'll square it. We'll throw our dx out at the end, and we get 407.150. And that is our final answer. It's worth 3 points here. 1 for the correct limits and constant, 1 for the correct integrand, and 1 for the final answer. And that is the end of this area and volume FRQ. It was question number 1 from the 2004 Form B AP Calculus AB exam. All right, this is question number 6 from the 2004 Form B AP Calculus AB exam. This is another area and volume FRQ, the second one in this year. It's a little bit different though. We have L is a line tangent to the graph of x to the n at 1, 1, where n is greater than 1. Right? And we want to first find the integral from 0 to 1 of x to the n dx in terms of n. Well, to integrate x to the n, you just get x to the n plus 1 divided by n plus 1. And so if we evaluate that from 0 to 1, right, for our x values, when we plug in 1 to that, we get 1 to the n plus 1, which is 1 over n plus 1. And then minus 0 to the n plus 1, which is just 0. So really, we just get 1 over n plus 1. So pretty straightforward one there. They gave you 2 points for that, 1 for the correct antiderivative and 1 for the correct answer. In part B, it says T is the triangular region bounded by that line, the x-axis, and x equals 1. We want to show that the area of T is 1 over 2n. Well, we know this is a triangle, right? So that the area of any triangle is just 1/2 the base times the height. And so we just need to figure out what the base and the height are. Well, the height, right? We know that this line is tangent at 1, 1. So the height here, right? This is just going to be 1. So we've now got 1/2 of the base times 1. And we need to figure out what that base is, right? So that base here is, if this is from x equals 1, right? It's just this distance. We'll mark it here. This is 1. So it's just 1 minus whatever the x-intercept of that line is, right? And so in order to figure out what the x-intercept of that line is, we need to know what the slope of that line is, right? And so the slope of that line, well, it comes from the derivative of the function x to the n at x equals 1. And so the slope of the tangent line there, like we said, it's just the derivative, right? Y prime is just n x to the n minus 1. And so if I'm going to evaluate that at 1, well, we're just going to get n there, right? So we know that the slope of that line is n. And if the slope of that line is n, we can write the equation of the tangent line, y minus 1 equals n times x minus 1. And all we're looking for then is what the x-intercept is, which is when y is equal to 0, right? So we want the x-intercept. So when y is 0, we get negative 1 equals n x minus n. Or in other words, that intercept is going to be nx equals n minus 1, or x is equal to n minus 1 over n. And well, what we're doing here is that's the intercept. So this distance here is n minus 1 over n. And so this distance here for our base is 1 minus n minus 1 over n. And of course, if we simplify that down, we can see that's just 1 minus n over n is 1, and then minus 1 over n. And if I distribute that through, we just get 1 over n, right? 1 minus 1 is 0, and negative 1 over n is 1 over n. So we end up with 1 over n as our base, telling us that that area is 1 over 2n, just like it wanted us to show. And they gave us 3 points for that. 1 point for showing that the slope of the line was n, 1 point for showing that the base was 1 over n, and 1 point for showing the area here using the formula for a triangle, that it was 1 over 2n. And here in part C, it says, now S is the region bounded by the graph of y equals x to the n and L and the x-axis. We want to express the area of S in terms of n, and then determine the value of n that maximizes the area of S. Well, in order to do that, we just need to write out a function that represents the area of S in terms of n. So the area of S in terms of n is just going to be, we'll write it as a of x, right, is just the function, it's the integral of the function, right, from 0 to 1. Minus the area of the triangle. So the area of that triangle was 1 over 2n. And we already know that the integral of x to the n, we already did that earlier. The integral from from 0 to 1 of x to the n was just 1 over n plus 1. So the area is 1 over n plus 1 minus 1 over 2n. And so now what we want to know is we want to know what value of n maximizes this area. So that's an optimization question, right? We want to know when is that function at a maximum. So we need to take the derivative, right, of 1 over n plus 1 minus 1 over 2n. So we're going to do the derivative with respect to n of 1 over n plus 1 minus 1 over 2n. And so the derivative of 1 over n plus 1, that's like n plus 1 to the negative 1. So it's negative 1 times n plus 1 to the negative 2, or negative 1 over n plus 1 squared. And then the derivative of negative 1 over 2n, that's just, if you think about that, that's negative 1 over 2 times 1 over n. So just take the derivative of 1 over n, which is negative 1 over n squared, and keep the negative 1/2 out there. So that just becomes plus 1 over 2n squared. So we want to know when is that undefined and when is that equal to 0. Well, it's equal to 0 at 0. It's undefined at 0 and at negative 1. Negative 1 we don't care about. And 0, right, is the value right here, right? So that's not going to make any sense either, right? Because we said that our value of n has to be greater than 1, right? And so neither of those are going to make any sense. So really we just want to see when does this equal 0. So what we'll do is we'll just add the 1 over 2n squared to the right-hand side. And then we can cross multiply to get 2n squared equals negative 1 over n plus 1 squared. This was a plus, right? So really we don't have that negative there, right? That was a plus. We said this was positive 1 over 2n squared. So just make sure you get that positive there. Now when we bring the terms on opposite sides and cross multiply, I've written this all horribly. When we cross multiply, we get 2n squared equals n plus 1 squared. And, we'll just square root both sides of this. We're running out of room here. So if we square root both sides of that, right, we had 2n squared equals n plus 1 squared. That gives us root 2n equals n plus 1. And of course, we can just get all the n's on one side. So it'll be root 2n minus n equals 1. Factor out the n. And if we factor out the n, we've got root 2 minus 1 equals 1. And n is 1 over root 2 minus 1. And of course, if you want to, you can simplify that down by multiplying by the conjugate. But actually, it'll look kind of nice if we do that. So let's do that just for the heck of it. You don't need to do that, right? If you multiply by root 2 plus 1 and root 2 plus 1, well, on the top, you're going to get root 2 plus 1. And in the bottom, you end up with a root 2 times root 2 is 2. And then the middle terms cancel out, and you just have minus 1 down there. So really, you just get 1 plus root 2. And that's going to be the value at which this thing is going to be at its maximum. And so you got 4 points there in part C. 1 for the area of S here. A second one for the correct derivative. A third one for just setting the derivative equal to 0. And a fourth one for getting down here to the final value where you solve for n. And that is the end of this area and volume FRQ. It was question number 6 from the 2004 Form B AP Calculus AB exam. All right, this is question number 1 from the 2005 AP Calculus AB exam. This is a area and volume FRQ. It's a calculator question where we're given 2 functions, f and g, right? Defined as 1/4 plus sine pi x for f and 4 to the negative x for g. And R is the region in the first quadrant between them and the y-axis. And then S is the rest of the region between them in that first quadrant right there. And we can see it in the figure. And we want to first just find the area of region R. Well, the area of region R should just be the integral of the upper function, which we can see is g of x, minus the lower function, which is f of x dx, from 0, because we're starting at the y-axis, to whatever this intersection point here is. And since this is a calculator question, we'll just set them equal to each other on our calculator and see where that intersection point is. So we'll go to our graphing calculator. We'll graph the two functions. So the first function was 1/4. So I'm just going to put 0.25 plus the sine of pi x. And then our other function was 4 to the power of the opposite of x, 4 to the power of negative x. And when we graph them, we can see, maybe we might want to zoom in just a little bit there. I'm just going to change my window here. I'm going to hit the window button. I'm just going to go from -1 is my x min to 2 is my x max, because it looks like that was probably sufficient to find that point. Actually, let's go a little further, and let's go to like 5, and then we'll graph it. That way, yeah, okay. So that's plenty good here. So we'll do second trace, and we want the intersection point. And so we're going to scroll way over here. It's going to take a second here. We want to find this intersection point over here. We'll hit enter. Once we get a little to the left of it, go to a little to the right, hit enter, and hit enter once more, and we get 0.178218. So that's our first intersection point. And that's the one we need for this particular part of the problem. But it would also be good to find that other intersection point, because we're probably going to need it at some point. Otherwise, why else would they have us be dealing with region S? So let's find that one real quick. Second trace, option number 5 again for intersect, and now go over towards that second intersection point. Hit enter, go a little past it, and we'll see this time that it actually comes out to be a real nice value. It's just x equals 1. So we'll note that that's at x equals 1. So now we do need to evaluate this integral to get our final answer here in part A. So once again, we'll just go back to our calculator. We'll hit second quit, and we will hit math, option number 9, to do an integral here. And it's going to go from 0 to that intersection point that we found at 0.178218. And then it's just the upper function minus the lower function. And that was g minus f. Well, we had g plotted as our second function. So I'm going to hit VARS, go over to the second column, hit 1 for option 1 there for the functions, and then go down to the second one, because that was g of x. And then I'm going to do the same thing, VARS, second column function, and now I want f of x, which was y1. That way I don't have to retype the functions, and I just get 0.065 when I round. And that was worth 3 points, 1 for the correct limits, 1 for the correct integrand, and 1 for the final answer. In part B, it just wants us to find the area of S. So we're just going to do the same thing. We're going to integrate from that 0.178218 to 1, right? Because now we're going from here to here. But this time it's not g minus f. This time it is f minus g, because on this interval, f of x is above g of x. Right? We can see f of x is above g of x here. So we'll just go back into our graphing calculator. We'll hit math and option number 9. And again, you can just hit the 9. You don't have to scroll down to it. And we're going to go from 0.178218 up to 1. And this time we want y1 minus y2. So we'll hit VARS, second column function, y1 minus VARS, second column function, number 2, our second function y2 dx, and we get 0.410. And that was also worth 3 points. 1 for the right limits, 1 for the right integrand, and 1 for the right answer. And then in part C, it asks us to find the volume of the solid generated if we revolve S around the horizontal line y equals -1. So here's y equals -1, and we should know that when I revolve that around there, since that region S, is not fully pushed up against the line y equals -1, we end up with washer cross sections, right? We end up with something that looks about like this for each cross section. All right, we get these big washers. All right, so we're looking for the outer radius, which is going to be the distance from the upper bound of the region down to y equals -1. So that's our outer radius, which is going to be 1 unit to get up to the x-axis, and then f of x units after that to get up to the top of the region. So 1 plus f of x is our outer radius. And then our inner radius is going to be from the lower function to -1. So that'll be 1 plus g of x, right? We're going up 1 unit, and then we're going up g of x units. And so the method we use here is our washer cross sections, pi times the integral of the outer radius squared minus the inner radius squared. So we're going to integrate from that same value we had before of 0.178218 to 1 of our outer radius, 1 plus f of x squared minus 1 plus g of x squared dx. And we'll just put this into our graphing calculator once again to get a final answer. So don't forget your pi out in front. Common for people to forget that. Math option number 9 to get your integral. We're going to go from 0.178218 again up to 1. And now inside of our integral, I'm going to make a new parenthesis for my first radius, which was 1 plus f of x. So we'll go in that same way we've been doing, VARS over to the second column, function number 1. And we'll square that. And then minus, and then a parenthesis for our second one, 1 plus, same thing, VARS, second column. Now we want y2 squared, and then dx out there at the end. And we end up getting 4.559 as our final answer. And once again, this part was worth 3 points. 2 points for the correct integrand, and 1 point for the final answer. That's all 9 points for this area and volume FRQ question number 1 from the 2005 AP Calculus AB exam. All right, this is question number 1 from the 2005 Form B AP Calculus AB exam. It's a calculator question, and it's an area and volume one. So we've got two functions, f and g. F is 1 plus sine 2x, and g is e to the x over 2. And R is the region in the first quadrant between them. And so we want to find the area of R. So in order to do that, we just have to integrate the upper function minus the lower function. So we're just going to integrate f of x minus g of x from the first intersection point to the second intersection point. Now, I think we should be able to tell that if I plug in 0 to each of these, right, if x equals 0, that's going to be our first intersection point. Now, we could use our calculator to figure that out, but the sign of 0 is 0, so that's just 1. F of 0 is 1, and g of 0 is also 1, because e to the 0 is also 1. But we do need our calculator to figure out that second intersection point. So we'll go to our graphing calculator, we'll hit y equals, and we'll do our first function will be 1 plus the sine of 2x, and that's f of x, right? And our g of x function was just e to the x over 2. Oops. X, let's fix that, e to the x over 2. There we go. And we'll graph those. And we'll look for our intersection point by hitting second trace and option 5 for intersect. And we'll scroll over pretty close to the first intersection point, hit enter, and go to the right and hit enter again, and one more time, and we end up with 1.13569525. And just in case we need it, I like to always note the y value here for that. Right, the y value there is 1.7644628. So we'll note that down too, just in case we need that later on. So we'll have that just in case. So now I'm going to call this A here. I'll call this B just in case I need it later. And now I'm going to integrate from 0 to A of f of x minus g of x dx. So in our calculator, we'll hit second quit. We'll do math, option number 9. And we're going to go from 0 to our A value, which was 1.1356925. And we're going to integrate the upper function minus the lower function, which was 1 plus the sine of 2x, and then minus e to the x over 2. Put our dx out at the end, and we get 0.429. And they gave you 3 total points there. 1 just for having the correct limits in this integral, 1 for the correct integrand, and 1 for the final answer. And if you had the wrong limits in part A, as long as you had the right limits in parts B or C, you'd get that point. In part B, we're looking for the volume of the solid generated if we revolve R about the x-axis. So if we're going to revolve this around the x-axis, right, we're going to end up with washer cross-sections, right? We're going to end up with these washers, right, because we're going to revolve around that x-axis, that region. And so we're going to have, since the region is not fully pushed up against the x-axis, we end up with this gap in the middle. Right? And our outer radius is always going to extend, right, from the upper bound to the x-axis. Well, that's just that function f of x. And then our lower bound is going to give us our inner radius, right? Our inner radius is just going to be g of x. And so washer cross sections give us pi times the outer radius squared minus the inner radius squared. So we'll do pi times that integral from 0 to a of our outer radius squared, which is f of x, squared minus the inner radius, which is g of x, squared dx. And you don't necessarily need to write out the f of x minus the g of x, right? You can just keep the f of x and the g of x as is, and then we'll go in here and go to our graphing calculator, and we'll do math option number 9, and don't forget your pi out in front. So I'm going to hit second insert and put my pi out there because I almost forgot it, which is a common thing to forget. And we're going to put in our 1.1356925 there. And then on the inside here, this time instead of rewriting each of those functions, I'm going to hit the VARS button next to clear and go over to the second column and hit function, and then y1 was f of x. So I'm going to do y1 squared minus, and then I'll do the same thing again. So I just so I don't have to rewrite it, I'll retype it with the squareds. Same thing, VARS, second column function. Now I'm going to choose y2 because that's where I put g of x, and then I'll square that, and I'll hit dx, and we end up with 4. I didn't even look at it. 4.267 when we round. And you got 3 points there. 2 points for the correct integrand and 1 point for the correct answer. In part C, we now have a volume by cross sections problem. So it says the cross sections perpendicular to the x-axis are semicircles with diameters extending across the region. So we have semicircles protruding out of the screen towards you here. And we know that the area of a semicircle is always going to be 1/2 of pi times the radius squared. And it tells us that the diameter is what's extending across the region. So that's the diameter equal to f of x minus g of x, the upper function minus the lower function, which means our radius is going to be 1/2 of f of x minus g of x. And so now we just plug that into our area formula and integrate from 0 to that same a value. So we're going to have a 1/2 pi, and then times our radius squared, which is 1/2 of f of x minus g of x. And I think it's simpler if we just pull all the constants out into the front, right? So we have a 1/2 pi, plus we have another 1/2 that's being squared. So that's 1/2 pi times 1/4, which is going to be a pi over 8 out in front, times our integral from 0 to a of f of x minus g of x squared. And we'll just use our calculator to evaluate that. So we'll put our constant out in front, pi over 8. And then we hit math, option number 9 for our integral. We're going to go again from 0 to a, which was 1.1356925. And we're going to use the same trick we used before with the VARS button. We'll hit that, go over to the second column, and we'll do y1 minus y2. So we'll do the same thing again, VARS in the second column. And then we will square f minus g, put our dx outside, and we end up with 0.078 when we were. And that was worth 3 points in part C, 2 points for the integrand, and 1 point for the final answer. And that is the end of this area and volume FRQ, question number 1 from the 2005 Form B AP Calculus AB exam. All right, this is question number 1 from the 2006 AP Calculus AB exam. It's an area and volume FRQ. And what we're looking at here is the function y equals ln of x and the line y equals x minus 2, and we want to find the area of the region between them. This is a calculator question, so all we have to do is figure out where they intersect, and then we will just integrate the upper function minus the lower function from the intersection points. And so we will go into our graphing calculator here. We'll put in y equals the natural log of x, and the other function was x minus 2. So we'll just graph those two functions, and we'll find their intersection points. And so we'll do second trace, and then we'll find option 5, intersect. And we will hopefully be close enough here to find this intersection point. Just hit enter a couple times there. And it looks like our intersection point is at 0.1585943. So we'll put that in here. So we'll say ln x equals x minus 2 when x is 0.1585943. Then we'll go back to our graphing calculator here. Again, we'll hit second trace. We'll do intersect again. This time we'll scroll over close to the other intersection point and hit enter, and go a little past it and hit enter. And one more time, and it will tell us it's 3.1461932. And I'm going to just call those A and B so I don't have to keep rewriting them every time. And our upper function is clearly natural log of x, where our lower function is x minus 2. So to find the area between them, we just integrate from A to B, the natural log of x minus x minus 2 dx. And we'll do that on our calculator. So we'll hit second quit. We'll hit math, option number 9. And our limits here were 0.1585943 and 3.1461932. And we're just integrating natural log of x minus the quantity x minus 2 dx. And it looks like we get 1.949. And part A there was worth 3 points. 1 for the correct integrand, 1 for the correct limits of A and B, and 1 for the final answer. In part B, it says find the volume of the solid generated if we take R and rotate it around the line y equals -3. So when we rotate around y equals -3, because that region R, is not fully pushed up against that line, we end up with washer cross sections. And our radius will extend, our outer radius will extend from the upper function down to y equals -3. That's going to be our outer radius. And our inner radius is going to extend from the lower function down to y equals -3. And so for each of those, it's just those 3 units plus the function. So the lower bound of the region is x minus 2, so this one will be 3 plus x minus 2, or just x plus 1. And then this one will be 3 plus ln of x. And the washer cross sections, remember, right, they look like this, right? It's pi times the outer radius squared minus pi times the inner radius squared. So we'll do pi, and then we'll integrate from a to b. Our outer radius squared, so 3 plus ln of x squared, minus our inner radius, which we just now said was x plus 1 squared dx. And if you wrote 3 plus x minus 2, that's also fine, doesn't really matter. And then we'll just use our calculator to evaluate that. So biggest mistake is people forget their pi out in front, so don't forget your pi. Then it's math option 9. You don't have to scroll down, you can just hit the 9. And our limits here were 0.1585943 and 3.146192. And our first radius there, we'll put it in parentheses, it was 3 plus the natural log of x. And we need to square that. And then we'll subtract the other radius, which was x plus 1. And we'll square that. We'll throw our dx out at the end. And our calculator tells us that is 34.199. And part B there was worth 3 points. 2 points for the integrand, 1 point for having the right limits and constant that allowed us to get the correct final answer. Here in part C, it wants us to write but not evaluate an integral expression that we could use to find the volume of the solid if R is rotated around the y-axis. And so if we're going to go around the y-axis here, right, what we want to do here is we want to probably do a washer cross-section, but we're going to do a washer cross-section where we do it in terms of y, right? So our outer radius here is going to be the distance to the rightmost function, which if we had y equals x minus 2, that's the same as x equals y plus 2. And our inner radius is the leftmost function. From y equals ln x, that becomes x equals e to the y. So our outer radius is going to be y plus 2, and our inner radius is going to be e to the y. So it's going to look like pi times an integral of our outer radius, y plus 2, squared, minus our inner radius of e to the y, squared dy. And then we need limits of integration. Now, we didn't write down what those limits of integration were, or what our intersection points, our y values of our intersection points were. But since we know that the x values were a and b, right, we can't go from a to b, but the y values of each of them just needs to be 2 less than the x values, right? Because they both satisfy this equation. So if the a value was 0.1585943, then the y value associated, that would just be a minus 2. And the same here for the b value, right? We'll just subtract 2 from it, and we should have the y coordinate of where those intersected. And so this is perfectly acceptable. If you want to write out a minus 2 and b minus 2, the actual values, that's fine too. But this answer would get you full points. In fact, it gets you all 3 points here. 2 points for the integrand and 1 point for the pi and the correct limits. So 3 points there for that one. And that's the end of this area and volume FRQ. Was question number 1 from the 2006 AP Calculus AB exam. All right, this is question number 1 from the 2007 AP Calculus AB exam. It's an area and volume FRQ, where we're given R is the region in the first and second quadrants, bounded above by y equals 20 over 1 plus x squared, and below by the horizontal line y equals 2. And so we first want to find the area of R, and we can do this without graphing it because we know it's bounded above by that function and below by the line y equals 2. It's a calculator question, so we can just graph them and see where we intersect, but I think it's good practice just to do the algebra real quick anyway here. Just set 20 over 1 plus x squared equal to 2, right? And then when you, you can cross multiply here basically, and then divide by the 2, you end up with 10 equals 1 plus x squared. Which tells us that x squared equals 9, or x is positive or negative 3. And we will eventually evaluate this integral using our calculator, right? Because what we end up with is, since the upper function is 20 over 1 plus x squared, and we're going to subtract the lower function of 2 from it and integrate from negative 3 to 3, because that's our bounds that we just found. Right? That's an inverse tangent integral, and we're not going to be able to find by hand the inverse tangent of 3 or the inverse tangent of negative 3. So now we'll just go to our graphing calculator. We'll hit math. We'll go down to option number 9, and we'll integrate from negative 3 to 3. I'm going to hit alpha x to give me a nice fraction. If your calculator doesn't have that capability, then just make sure you put that whole fraction and its denominator into parentheses. And then we'll just put in our function with a dx out at the end, 20 over 1 plus x squared minus 2 from negative 3 to 3, and we get 37.962. And that question, part A there, was worth 3 points, 1 for just finding these correct limits, 1 for the integrand setup, and 1 for the final answer. In part B, it asks us to find the volume of the solid generated if we take R and rotate it about the x-axis. Now, we might not know what 20 over 1 plus x squared looks like, but it doesn't really matter what it looks like. We're going to graph it just so you can see it, right? If we do 20 over 1 plus x squared, we can see that what that looks like is just, it's like a bell curve, right? That's basically what we've got here. And we can't see the y-intercept there of 20. If we want to, we can change our window so that our y max is now 20, right? And then we can see the whole thing. And of course, y equals 2. If we were to graph that, we can see that we know that's just a horizontal line. So we're taking this region between the two of them, right? And we're going to revolve it around the x-axis. So I'm just going to draw a basic sketch here. We got something that looks like this and this. So we're talking about this region right here being revolved around the x-axis. Right? And since this region is not fully pushed up against the x-axis, we end up with washer cross-sections. Right? When we revolve around, we get these circles with circles cut out of the middle of them. Right? Where the outer radius extends from the upper bound of the region down to the x-axis. Right? That's going to be our outer radius, and then the inner radius just extends from the lower bound to the axis that we're revolving around. That's our inner radius. And our inner radius is just going to be 2 units, right? Because we're going from the x-axis to the line y equals 2. And our outer radius is just going to be the distance from the x-axis to the function, right? The outer is just y, or it's just 20 over 1 plus x squared. And so in order to find the area of a circle, right, it's pi times the radius squared. So we're going to do pi times the outer radius squared minus pi times the inner radius squared. And then we're going to integrate that from -3 to 3. So we'll put our pi out in front. Our limits will be -3 to 3. We'll do our outer radius of 20 over 1 plus x squared and square it. And subtract our inner radius of 2 squared. And then we'll just use our calculator to evaluate this. And I find that oftentimes people forget to put their pi out in front, so just make sure you get that pi out in front. And then we're going to hit math, option 9. Again, you can just scroll down to the 9, or you can just hit 9. We're going to integrate from -3 to 3. And we want to do, this time we want to put this first function, I'm going to put it in parentheses, 20 over 1 plus x squared into parentheses so that I can then square it, right, because it's that radius squared, and then -2 squared, or -4, dx. And it looks like we get 1,871.190. And that was worth 3 points, 2 points here for the correct setup, and 1 point for the final answer, right? 2 points for just the integrand portion of it. So if you forgot the pi, you still get 2 points out of the 3. In part C, we've got region R, which is the base of a solid, and the cross sections perpendicular to the x-axis are semicircles. We want to find the volume. Well, I'm just going to sketch another quick graph of this, right? It just, it looks like this again, right? The cross sections perpendicular to the x-axis of the solid are semicircles. So forgive my terrible drawing here, but basically what we've got is no matter where I slice this thing vertically, right, perpendicular to the x-axis, if I were to open up the face of it and look at it, I'd look at a semicircle face. Right? In other words, I have these semicircles essentially protruding straight out of the screen towards you, which my 3D drawing skills are leaving a bit to be desired here. But that's what I'm attempting to draw, is that these are all semicircles that are stretching across the region with the diameter equal to the distance between the two functions, right? And the diameter then is 20 over 1 plus x squared minus 2, right? It's the distance between them, right? The upper function minus the lower function. And that's where one of the major mistakes that people make on these semicircular cross sections is they equate that distance across the region to the radius, but it's not the radius, it's the diameter, right? So our radius of the semicircle is 1/2 of 20 over 1 plus x squared minus 2. And so now we just need to integrate the area of each of those cross sections from -3 to 3. And the area of a semicircle is 1/2 pi times the radius squared, right? So my area, and I'll write this down here, it's 1/2 pi times 1/2 of 20 over 1 plus x squared minus 2 squared. So we're going to note that we're going to have a constant here of pi out in front over the 1/2 and the 1/2 squared, so pi over 8 out in front. And then I'm going to have on the inside 20 over 1 plus x squared minus 2 still being squared. And of course, if you just put this in as your integrand, that's fine. But I like to pull the constant out to the front. So we'll go back to our graphing calculator. I'm going to put that pi over 8 out in the front. I'm going to hit math, and I'm going to go down to option number 9. We're going to integrate from -3 to 3. And what we need to have inside of there, I'm going to put it all in its own parenthesis again. 20 over 1 plus x squared minus 2, all being squared. And then we've got our pi over 8 out in front. And we end up with a final answer of 174.268. And that also was worth 3 points. Once again, 2 for the correct setup with the integrand and 1 for the final answer. And that is the end of this area and volume FRQ. It's question number 1 from the 2007 AP Calculus AB exam. All right, this is question number 1 from the 2007 Form B AP Calculus AB exam. It's an area and volume FRQ where we're looking first here for the area of region R, right? And R is bounded by e to the 2x minus x squared and the horizontal line y equals 2. Region S, which we'll deal with in other parts, is just the part between y equals 1 and y equals 2 of e to the 2x minus x squared. So first we want to find the area of region R, which means we need to figure out, first of all, when does e to the 2x minus x squared equal 2? Now, we'll just use our graphing calculator here because this is a graphing calculator question. So I'm going to hit y equals. My function is e to the 2x minus x squared. And I also want to see when that intersects with y equals 2. So we'll just graph both of those. And we'll hit second trace, option 5 for intersect, and go kind of close to that intersection point and hit enter. Go a little past that intersection point and hit enter. And our first value is 0.446057. So we'll make a note of that. X equals 0.446057. And then we'll find the other one also. And I'm just going to call this A so I don't have to keep rewriting it. So to find the other one, we'll hit second trace, option 5 again, intersect. Go close to that second intersection point, hit enter. Go just past it, hit enter. Hit enter a third time, and you get 1.553943. And I'll call that B. And if we want to find the area of region R, well, we just have to do the upper function minus the lower function integrated from A to B. Well, the upper function is clearly e to the 2x minus x squared. We'll subtract 2 from it, and then throw our dx off of there and integrate and get a value. So we're just going to go to our graphing calculator here. We'll hit second quit to go out of there. Math option 9 gives us that integral. We're going from the first intersection point, which was 0.446057, to our second intersection point, which was 1.553943. And it was just our upper function of e to the 2x minus x squared. And then minus our second function, which was just 2, dx. And that gives us 0.514 when we round. So we'll just say 0.514. There's our final answer for part A. We got 3 points, 1 for the correct integrand, 1 for having the right limits of A and B, and 1 for the final answer. In part B, it wants us to find the area of S. Well, we've already got 2 of our intersection points here, right? We already have the intersection points that we're going to need here, right? A and B, right? So we've already got those, but we do need this one, which this one's clearly 0, right? We can see that if we plug in 0 to, right, e to the 2x minus x squared, right? If we set e to the 2x minus x squared equal to 1, we know one of those things that we're going to get is x equals 0. We do need to find this other one, though, right? We need to find this one out here. So we'll go back to our graphing calculator. This time, we'll get rid of this 2 here. We'll just turn it into a 1, and now we'll graph. And like I said, we already know that first intersection point is 0. So we'll just hit second trace, option 5 for intersect. And we'll go over close to that other intersection point, hit enter, go a little past it, hit enter, and hit enter a third time, and we get, that intersection point there is 2. We probably could have seen that if we just kind of thought about this, right? That e to the 4 minus 4 is e to the 0 also, which is just 1. So that intersection point is 2. Make sure you write this and this statement of how you're finding x equals 0 and x equals 2, because they like to see that. And now we have to break this down here into a couple of different little integrals here, or we can just do the area from 0 to 2 here, right? Do this whole area and then subtract off our answer that we got for region R. Now, the other option is to separate it into this little chunk and then this chunk here in the middle, right? And so we can do it as 3 different little pieces, or we can do it as that whole big piece minus region R. So I think we'll show the setup for both. I'll only evaluate one of them. But if I want to do the setup for both, if I do the setup for, let's say, the whole thing, let's do the whole thing first, right? That integral is going to be the integral from 0 to 2 of the upper function, e to the 2x minus x squared, minus the lower function, 1. And then we just have to subtract the area of region R, right? The other option would be to integrate from 0 to a of e to the 2x minus x squared minus 1. And then we would add to that the distance between a and b here, right, times 1, so plus 1 times b minus a, right, because that's going to be just a rectangle there. And then we would add to that the integral from b to 2 of e to the 2x minus x squared minus 1 dx. And either way you do it, you're going to get the same answer. I'm just going to evaluate it on the first one there. So if we go back to our graphing calculator and we do math option number 9, we've got we've got our limit of 0 and our second limit of 2, and now inside of here we've got e to the 2x minus x squared minus 1 dx, and then we have to subtract that first area that we found. So I'm just going to hit minus, and I'm going to go up here and highlight that one and hit enter, and it'll just populate it down below. We'll hit enter, and we get 1.546 when we round. And if you do it the other method, you're going to get the exact same value. So for that one, you got 3 points, 1 for the correct integrand, 1 for the correct limits, and 1 for the final answer. And for our last one here, we're just going to see what happens if we revolve region R around the horizontal line y equals 1. Right, so we're taking region R, which is not fully pushed up against that line y equals 1, and revolving it around, which means we're going to get these washer cross sections because we've got a gap in the middle. So if we revolve around y equals 1, our outer radius is just going to extend from the upper region to, or the upper bound of our region to 1, and the inner radius is just going to be the distance from the lower bound of that region down to y equals 1. So the lower radius is just always going to be equal to 1, but our outer radius, right, since we're just going from 1 to 2 there, but our outer radius here is going to be the entire distance from the x-axis up to the function, which is just the function, e to the 2x minus x squared. But then we have to subtract off this little bit here, this 1 unit below. So e to the 2x minus x squared minus 1. And so our washer cross sections look like pi times the integral from the left bound to the right bound. And we defined those earlier as a and b. So it's the integral from a to b of our outer radius, e to the 2x minus x squared minus 1 squared, minus our inner radius of 1 squared dx. And that should be your final answer. And they gave you 3 points for that one. They gave you 2 points for having the correct integrand, and 1 point for having the constant of pi with the correct limits from A to B out in front there. And that's the end of this area and volume FRQ. Is question number 1 from the 2007 Form B AP Calculus AB exam. All right, this is question number 1 from the 2007 Form B AP Calculus AB exam. It's an area and volume FRQ where we're looking first here for the area of region R, right? And R is bounded by e to the 2x minus x squared and the horizontal line y equals 2. Region S, which we'll deal with in other parts, is just the part between y equals 1 and y equals 2 of e to the 2x minus x squared. So first we want to find the area of region R, which means we need to figure out, first of all, when does e to the 2x minus x squared equal 2? Now, we'll just use our graphing calculator here because this is a graphing calculator question. So I'm going to hit y equals. My function is e to the 2x minus x squared. And I also want to see when that intersects with y equals 2. So we'll just graph both of those. And we'll hit second trace, option 5 for intersect, and go kind of close to that intersection point and hit enter. Go a little past that intersection point and hit enter. And our first value is 0.446057. So we'll make a note of that. X equals 0.446057. And then we'll find the other one also. And I'm just going to call this A so I don't have to keep rewriting it. So to find the other one, we'll hit second trace, option 5 again, intersect. Go close to that second intersection point, hit enter. Go just past it, hit enter. Hit enter a third time, and you get 1.553943. And I'll call that B. And if we want to find the area of region R, well, we just have to do the upper function minus the lower function integrated from A to B. Well, the upper function is clearly e to the 2x minus x squared. We'll subtract 2 from it, and then throw our dx off of there and integrate and get a value. So we're just going to go to our graphing calculator here. We'll hit second quit to go out of there. Math option 9 gives us that integral. We're going from the first intersection point, which was 0.446057, to our second intersection point, which was 1.553943. And it was just our upper function of e to the 2x minus x squared, and then minus our second function, which was just 2, dx. And that gives us 0.514 when we round. So we'll just say 0.514. There's our final answer for part A. We got 3 points, 1 for the correct integrand, 1 for having the right limits of A and B, and 1 for the final answer. In part B, it wants us to find the area of S. Well, we've already got 2 of our intersection points here, right? We already have the intersection points that we're going to need here, right? A and B, right? So we've already got those, but we do need this one, which this one's clearly 0, right? We can see that if we plug in 0 to, right, e to the 2x minus x squared, right? If we set e to the 2x minus x squared equal to 1, we know one of those things that we're going to get is x equals 0. We do need to find this other one, though, right? We need to find this one out here. So we'll go back to our graphing calculator. This time, we'll get rid of this 2 here. We'll just turn it into a 1, and now we'll graph. And like I said, we already know that first intersection point is 0. So we'll just hit second trace, option 5 for intersect. And we'll go over close to that other intersection point, hit enter, go a little past it, hit enter, and hit enter a third time, and we get, oh, that intersection point there is 2. We probably could have seen that if we just kind of thought about this, right? That e to the 4 minus 4 is e to the 0 also, which is just 1. So that intersection point is 2. Make sure you write this and this statement of how you're finding x equals 0 and x equals 2, because they like to see that. And now we have to break this down here into a couple of different little integrals here, or we can just do the area from 0 to 2 here, right? Do this whole area and then subtract off our answer that we got for region R. Now, the other option is to separate it into this little chunk and then this chunk here in the middle, right? And so we can do it as 3 different little pieces, or we can do it as that whole big piece minus region R. So I think we'll show the setup for both. I'll only evaluate one of them. But if I want to do the setup for both, if I do the setup for, let's say, the whole thing, let's do the whole thing first, right? That integral is going to be the integral from 0 to 2 of the upper function, e to the 2x minus x squared, minus the lower function 1. And then we just have to subtract the area of region R, right? The other option would be to integrate from 0 to a of e to the 2x minus x squared minus 1. And then we would add to that the distance between a and b here, right, times 1, so plus 1 times b minus a, right, because that's going to be just a rectangle there. And then we would add to that the integral from b to 2 of e to the 2x minus x squared minus 1 dx. And either way you do it, you're going to get the same answer. I'm just going to evaluate it on the first one there. So if we go back to our graphing calculator and we do math option number 9, we've got we've got our limit of 0 and our second limit of 2, and now inside of here we've got e to the 2x minus x squared minus 1 dx, and then we have to subtract that first area that we found. So I'm just going to hit minus, and I'm going to go up here and highlight that one and hit enter, and it'll just populate it down below. We'll hit enter, and we get 1.546 when we round. And if you do it the other method, you're going to get the exact same value. So for that one, you got 3 points, 1 for the correct integrand, 1 for the correct limits, and 1 for the final answer. And for our last one here, we're just going to see what happens if we revolve region R around the horizontal line y equals 1. Right, so we're taking region R, which is not fully pushed up against that line y equals 1, and revolving it around, which means we're going to get these washer cross sections because we've got a gap in the middle. So if we revolve around y equals 1, our outer radius is just going to extend from the upper region to, or the upper bound of our region to 1, and the inner radius is just going to be the distance from the lower bound of that region down to y equals 1. So the lower radius is just always going to be equal to 1, but our outer radius, right, since we're just going from 1 to 2 there, but our outer radius here is going to be the entire distance from the x-axis up to the function, which is just the function, e to the 2x minus x squared. But then we have to subtract off this little bit here, this 1 unit below. So e to the 2x minus x squared minus 1. And so our washer cross sections look like pi times the integral from the left bound to the right bound, And we defined those earlier as a and b. So it's the integral from a to b of our outer radius, e to the 2x minus x squared minus 1 squared, minus our inner radius of 1 squared dx. And that should be your final answer. And they gave you 3 points for that one. They gave you 2 points for having the correct integrand, and 1 point for having the constant of pi with the correct limits from a to b out in front there. And that's the end of this area and volume FRQ. Is question number 1 from the 2007 Form B AP Calculus AB exam. All right, this is problem number 1 from the 2008 AP Calculus AB exam. This is an area and volume FRQ. We're given region R, which is the region bounded by sine pi x and x cubed minus 4x. So we want to first find the area of region R. That's the calculator problem, so we can just use our calculator to do the integral. We just need to be able to set it up. Right? And we can see that the upper function here must be the sine function, right? Because we know that if I plug in 1 to this sine function, I get the sine of pi, which is 0. Right? And if I plug in 1 to this, I get 1 minus 4, which is negative 3, which is clearly down here. Right? So we know the upper function is our sine function, so we're just going to integrate sine pi x minus the quantity x cubed minus 4x dx from the left bound of 0 to the right bound there of 2. And so we'll just put that into our graphing calculator and let it evaluate it for us, since this is a calculator question. We'll hit math, go down to option number 9. We're integrating from 0 to 2 of sine of pi x minus x to the third minus 4x. And we'll throw our dx down there, and we just end up getting 4. So we'll say that's equal to 4. And it's probably good for you to just write sine pi x equals x cubed minus 4x. That's true when x equals 0 and x equals 2, even though it's shown in the diagram. That way you have a little bit of work to show how you got those limits of integration. And they gave you 1 point for the correct integrand, 1 point for having the correct limits, and 1 point for the final answer. In part B, it says the line y equals negative 2 splits this region into 2 parts. All right, of course. And we want to write an equation, an expression, an integral expression that finds the area of the part of R that is below that horizontal line. So first we need to see when y equals negative 2 crosses through that region, right? And so that's the function x cubed minus 4x that it's hitting. So what we'll do is we will find out when x cubed minus 4x is equal to negative 2. And so the way we'll do that is we'll just go back to our graphing calculator and we'll graph x cubed minus 4x, and we'll graph y equals negative 2, and we'll see where they intersect. So we're looking for the area of this little region right down here that we could clearly see is just like what our picture showed from the actual test. So we're going to hit second trace. We're going down to option 5, intersect, and we'll find these values. We'll go kind of close to the intersection point, hit enter, go just past it and hit enter again, and then a third time. And we get 0.5391889. So we'll write that down here. X equals 0.5391889. And we know we have another point here, so we'll do that again. Second trace, option 5 for intersect. Go close over to that other intersection point, hit enter, go a little past it, hit enter, and we get, looks like 1.6751309. So we have our intersection points, and now we just need to integrate from the first one to the second one. And I'm just going to call this A and B so I don't have to rewrite them here. And you can do that on the AP test or on my tests. And we just want the upper function, which is -2, minus the lower function, which is x cubed minus 4x. And it says that we don't need to evaluate it. So that is our final answer. And they gave you 2 points for this, 1 for finding these limits correctly, and 1 for having the correct integrand. In part C, it tells us that region R is the base of a solid and that cross-sections perpendicular to the x-axis are squares. And we want to find the volume of this solid. Well, if the cross-sections perpendicular to the x-axis are squares, that means we've got these squares at every single x value here protruding out of the screen at you, right? And then we just need to sum together the cross-sectional area of each of those squares multiplied by the thickness of each one, which is just an infinitely small distance in the x direction. It's just dx. So the area of the cross-section is the side length squared. Well, the side length is always just the distance between the two functions, which is the upper function, sine pi x, minus the lower function of x cubed minus 4x. So all we have to do is integrate from 0 to 2, our upper function, sine pi x, minus our lower function, x cubed minus 4x. And of course, we need to square it because the area of each cross-section is the side length squared. And so we'll just use our calculator to find this value. We'll hit second quick to go back to the main screen. We'll hit math, go down to option 9. We're integrating from 0 to 2. And we're going to put inside of here the sine of pi x minus, and I'm going to put this second one in its own parentheses, right? X to the third minus 4x. Close that parenthesis. And then make sure that since I have that, I don't want to put my squared there. I need another parenthesis because I've put parentheses around the entire side length, sine pi x minus x cubed minus 4x. Then we'll square that with our dx out at the end. And that gives us, it looks like 9.978. And for that part, you got 2 points, 1 for the correct integrand and 1 for plugging it in and getting the right value in the end. In part D, it says that region R now models the surface of a small pond. And at all points in R, a distance of x from the y-axis, the depth of the water is 3 minus x. We want to find the volume of the water. Well, this is basically just a cross-sectional area problem here. The volume would be the depth times the times this distance across the region once again, right? Because that's just going to, we're looking for the volume of the water, right? That's going to be how far down it is at any given x value times the length of that section, right? These are just little cross sections that have an area of 3 minus x times the distance across the function. So we'll just integrate just like we did before, an integral from 0 to 2. This time, it'll be 3 minus x times that sine pi x minus the quantity x cubed minus 4x dx. So we'll just go in on our calculator and we'll just do that. We'll hit math. Option number 9, it's an integral from 0 to 2. First, we have our 3 minus x that I'll put in parentheses. And then I'll have my other function here, sine of pi x minus the quantity x cubed minus 4x. And let's see here. We need to close one more parenthesis there. or sine pi x minus x cubed minus 4x. Throw our dx out at the end, and we get 8.370. And they gave you 2 points there in part D, 1 again for the correct integrand, and 1 for the correct final answer. And that is the end of this area and volume FRQ, question number 1 from the 2008 AP Calculus AB exam. All right, this is question number 1 from the 2008 Form B AP Calculus AB exam. It's an area and volume question. All right, we've got region R is the region in the first quadrant bounded by root x and x over 3. And it just wants us to find the area of region R. Now, this is a calculator question. So you can go right ahead and just graph these on your graphing calculator to see where they intersect if you are concerned that you won't be able to do that by hand. Now, I think we could see that, I'm going to do it by hand, but we can see that obviously x equals 0 solves this, right? These both touch the origin, right? So we can say that's at x equals 0. And also, you know, if we just square both sides of this, right, we get x equals x squared over 9, or basically x squared equals 9x. Or when you do x squared minus 9x equals 0, you get x times x minus 9. So the other place they intersect is at x equals 9. And you know, you can do this on your calculator also, and I'll show that in a second. So really what we're going to do is just an integral from 0 to 9 of the upper function minus the lower function. Now, the upper function is root x, and the lower function is x over 3. Now, if you weren't sure about that, you could just test a value between 0 and 9 and see which thing is bigger. Like if you test 4, the square root of 4 is 2, and 4 over 3 is 1 1/3, so we can see root x is above. And since those are the only times they equal each other, it's got to be that root x is always more than x over 3 on that interval. And so we'll just go in real quick, and I'll show you how. So, you know, if we wanted to, root x and x over 3. And when you graph them, you can see that, you know, they've got 2 intersection points. You can see the origin there. And then if you wanted to, you'd hit second trace, intersect, and just kind of go scroll over a ways here until we're like fairly close to where they intersect. And hit enter. And then scroll over past where they intersect here and hit enter. And then hit enter one more time. You can see they intersect at the point 9, 3. So, you know, we were right. X equals 0 and x equals 9. And for x equals 9, that's the point 9, 3. We'll just note that. Now, we can also do this integral by hand, or since it's a calculator question, we can just do the integral on our calculator. So I'll hit second quit, and I'm going to hit math and go down to option 9 just to make sure I don't make an arithmetic error. Since I have the calculator, I might as well just put my calculator, or put my integral into my calculator. If you're going to do x over 3 here, I always make sure I put it in parentheses, or I hit alpha and then x to give myself this nice little fraction, just to make sure order of operations all works out fine on your calculator. We can see that we get, you know, 4.5 is the actual answer. Your calculator is doing its best to approximate. So it's got that 251 way off down at the end. But we'll just say this is equal to 4.5. And if you did it by hand, you'd see you get the exact same thing. We might want to note also that this can be done using y as well, right? So this answer is perfectly acceptable. But if I have root x, I'm going to just sketch it here, and x over 3, we could also do this in terms of y, right? If y is equal to x over 3, then x is equal to 3y. And if y is equal to root x, then x is equal to y squared. So we could have also done an integral from 0 to 3 from the bottom to the top of the line in terms of y, which is 3y, minus the root function in terms of y, which is y squared. So this would have also worked out. And if you punch that into your calculator or just do it by hand, you'll get 9/2 or 4.5 as well. So just something to note that we could have also done it in terms of y. Part A here was worth 3 points, 1 for correct limits on an integral, 1 for correct integrand, and 1 for the answer. In part B, it asks us to find the volume of the solid generated if we take R and rotate it around the vertical line x equals -1. And so here's where it's really nice to have already thought about this in terms of y, right? Because if I'm going to go around the vertical line x equals -1, well, that means that this is going to turn into washer cross sections for this solid that are all in the y direction, right? They have a thickness of dy. Because if I revolve this region here around, we get these washers that are infinitely thin in the y direction, which means this integral needs to be done in terms of y if we were going to use the washer method. Now, we could also use cylindrical shells, which is not a necessary topic for Calc AB, but something that I teach in my class, and it's sometimes very useful. So we'll show the setup for that as well in just a second. But we'll note that our outer radius here is just the distance from x equals -1 over to the rightmost function, which we already said was 3y. Right? And so the distance is now just 1 to get from x equals -1 to the y-axis, and then 3y. So that outer radius is going to be 3y plus 1, or 1 plus 3y. And the inner radius is going to go over to y squared, right? So it's going to be the 1 unit to get across here, plus the y squared, right? That part's y squared, and that part's 1, so our inner radius is 1 plus y squared. And when we have washer cross sections, it's pi times the outer radius squared minus the inner radius squared that we need to integrate from the bottom to the top. So we'll integrate from 0 to 3, the outer radius, 1 plus 3y, and then minus the inner radius, 1 plus y squared, dy. And they asked us to actually find this value, so we'll just go in. Make sure you put your pi out in front, then hit math option number 9, and we're going to integrate from 0 to 3, and I'm going to make sure to put each of my radii in their own parentheses, right? So we had 1 plus 3y. As our first one, we'll put x there, since this is everything has to be done in terms of x on your calculator, and then we'll do minus 1 plus y squared, or x squared for us, and make sure you square both those radii, throw your x out at the end, and we get 130.062. And as I said, we could have done this in terms of x using shells, right? We draw a little rectangle here and revolve that around the line x equals -1. Not quite how I drew that, right? Like this. And the radius would just be 1 plus x, right? So we'd have 1 plus x inside of an integral, and the height would just be the upper function minus the lower function, so root x minus x over 3. And we'd integrate this with a 2 pi out in front, right? Because the shell method says 2 pi times the radius times the height, right? And our radius is from -1 to here, so it's 1 unit to get to the y-axis and x over. And the height is just the difference between the two functions. We'd integrate from 0 to 9. And just to show that if we did this, we'd get the same thing, right? Here's 2 pi, math, option number 9. We're going to integrate from 0 to 9. And we had 1 plus x inside of there. And we also had times root x minus x over 3. There we go. Close that second parenthesis, dx. And we can see it should come out to be the same thing. The approximation is just ever so slightly off there at the end, but to 3 decimals, we're still good. And that was worth 4 points here. So, normally they're going to have their scoring guidelines using the disk or washer method because that's part of the curriculum for the course. So you have 1 point for the constant and the limits, 2 points for the integrand, and 1 point here for the final answer. Nothing wrong with doing it this way. You'd get the points also. But yeah, the scoring guidelines will show you how to do it using disks or washers. In part C, we're finding the volume of a solid if R is the base of the solid and the cross sections perpendicular to the y-axis are squares. So now we're looking at same thing, root x, and that was supposed to go through the origin. There we go. And x over 3. And the cross sections perpendicular to the y-axis are squares. So we've got like these little squares here protruding out of the board towards you, so that if I were to slice it perpendicular to the y-axis, we'd end up with squares, right? And so the area of each of those squares is just the side length squared. And all we have to do is integrate the side length squared from the bottom to the top, from 0 to 3. So we're going to integrate from 0 to 3 the side length squared. Well, we already found that side length. It was the rightmost function, which was 3y, minus the leftmost function, which was y squared. Right? The side length is just 3y minus y squared. So that's what we'll put inside of here. Again, you can do this without your calculator if you feel like it, but when you have a calculator at your disposal, you might as well use it and make sure you don't make an arithmetic error. So I'm just going to do math option 9 to get that integral. Put in my limits of 0 to 3, and I'll put 3x minus x squared, and then make sure I square it, right, for the side length squared, dx, and it looks like we get, kind of cutting it off there, but that turned into 8.1. There was actually nothing after the decimal there, so this was just 8.1. And it looks like that's the end here of this FRQ. And we got 1 point for the integrand, 1 point for the answer with the correct limits of 0 to 3. And that's the end of this area and volume FRQ. It was question number 1 from the 2008 Form B AP Calculus AB exam. All right, this is question number 4 from the 2009 AP Calculus AB exam. This is an area and volume FRQ where we have region R enclosed between 2x and x squared. And we want to find the area of that region, region R. So this one should be straightforward enough. Since we are given a graph, we know the intersection point is at 2, 4. We can just integrate from 0 to 2, right? The other intersection point being down here at the origin, 0, 0, of the upper function minus the lower function. And the upper function is clearly linear, right? So it's 2x. And the lower function is the parabola, x squared. So it's just the integral of 2x minus x squared from 0 to 2, which is x squared minus x cubed over 3 from 0 to 2. But when you plug in 2, you get 4 minus 8 thirds. And when you plug in 0 to both of those, you just get 0. So 12 thirds minus 8 thirds is 4 thirds. And part A there was actually worth 3 points. 1 for the correct integrand, 1 for the correct antiderivative, and 1 for the final answer. In part B, they ask us to find the volume here of this solid where region R is the base. And at each x value, the cross section of this geometric solid that's perpendicular to the x-axis has an area of sine pi over 2x. Well, this is just a volume by cross-section problem where normally they give you a shape and you have to find the area yourself, but this time there's no shape given, it's just the area. They tell you what that area of the cross-section is, so we just want to integrate the area of the cross-section across that interval, right? So we're just going to integrate sine pi over 2x from 0 to 2. Now, hopefully you can do this integral in your head without writing out the u sub, but if you need to write out the u sub, that's fine, right? U is pi over 2x, so du is just going to be pi over 2 dx, which means what we really need is a pi over 2 in here and a 2 over pi on the outside to cancel it out. Then I can turn the pi over 2 and the dx into just, well, I'll just write it off to the side. We'll write it off to the side. Inside of this integral, we just end up with sine u du, right? And so if I do that, the integral of sine u is negative cosine u. So I have negative, and I still have that 2 over pi cosine of pi over 2x. And we're just going to evaluate from 0 to 2. Okay. Well, plugging in 2 gives us negative 2 over pi and times the cosine of pi, and then minus the cosine of 0. And be careful not to make the mistake that a lot of people make, right? They say, oh, well, if I plug in 0, it's just 0. Well, no, if I plug in 0, it's the cosine of 0, which is 1. So what we've got is negative 2 over pi times the cosine of pi, which is negative 1 minus 1, or negative 2 times negative 2 over pi, which gives you 4 over pi. And that was worth 3 points. 1 for the correct integrand, 1 for the correct antiderivative, and 1 for the final answer. In part C, we've got a different solid, same base, right, region R, but this time the cross sections perpendicular to the y-axis are squares. So whenever the cross sections are perpendicular to the y-axis, the whole problem has to be done in terms of y. And so what we've got is a bunch of little squares, right, that are stacked together in this region that are perpendicular to the y-axis, right? And their area, of course, is just the side length squared. And the side length is just the distance in the y direct or in the x direction here between the two functions, right? It's the rightmost minus the leftmost, right? So we just need to figure out what those values are in terms of y. So if y is 2x, then x is y over 2. And if y is x squared, then x is root y. And our rightmost function is the curve, right? It comes from y equals x squared. So that's going to be our x equals root y. So we're going to integrate root y minus the leftmost function, y over 2. That's the distance across the region. That's the side length. So we square it because the area of the cross section is the side length squared, dy. And then, of course, our limits of integration here. We're not going to do 0 to 2 this time because we're doing it in terms of y. So we're going to do 0 on the bottom, but on the top, we're going to the upper bound, which is 4. And this was worth 3 points. 1 for the correct limits of 0 and 4, and 2 for the correct integrand. And that is the end of this area and volume FRQ. That was question number 4 from the 2009 AP Calculus AB exam. All right, this is question number 4 from the 2009 Form B AP Calculus AB exam. It's an area and volume FRQ, where we're given region R bounded by root x and x over 2. And we want to find first the area of region R. So they've given us the intersection point, which makes this really easy. We just have to do an integral from the left bound to the right bound, which is 0 to 4, of the upper function, which is root x, minus the lower function, which is x over 2. And you should be pretty clear on which one's the upper, right? Root x is a curve and x over 2 is a line. So it should be pretty obvious which is which. The integral of root x, we know, is just 2/3 x to the 3/2, right? Using the power rule, because root x is x to the 1/2. And then the integral of x over 2 is just x squared over 4. And we're going to evaluate from 0 to 4. Plugging in 4 first, right? Remember that we're going to do 4 to the 2/3. So we square root the 4 first, right? We do this bottom portion first. The square root of 4 is 2. When we cube the 2, we get 8, and then 8 times 2/3 is 16/3. And then minus 4 squared over 4, that's 16 over 4, or 4. And then when we plug in 0 to both of these, right, we get 0. So we just have 16 thirds minus 4. 4 is 12 thirds. So 16 thirds minus 12 thirds is 4 thirds. And that was worth 3 points. 1 for the correct setup, 1 for the correct antiderivatives, and 1 for the correct final answer. In part B, we've got the same region. It's the base of a solid. And the cross sections perpendicular to the x-axis are squares. And we want to find the volume. So that means that at every cross section perpendicular to the x-axis, if I were to slice this and then open it up, I'd be looking at a square. Right? Which means that, right, I've just got these little squares protruding straight out of the screen at you. An infinite number of them stacked all the way along this region, right? Infinitely thin in the x direction and stacked up against each other, making the full volume of this thing. And each one's area is just the side length of it squared. Well, the side length of it is just the upper function minus the lower function, right? Root x minus x over 2. And so if I want to find the volume, I'm just going to sum together using an integral from 0 to 4 the area of each of those squares, which is root x minus x over 2 squared. And so we're going to have to actually distribute this out. So we're going to have an integral from 0 to 4. Root x minus x over 2, we'll write this up here just to kind of look at it if that's helpful to you. Right? Root x times root x is just x. And minus x over 2 times minus x over 2 is positive x squared over 4. And then we have 2 of these root x times minus x over 2's. Right? So that's x to the 1/2 times x over 2. Well, that's going to be 1/2 x to the 3/2. And I've got 2 of those, and they're both negative. So really, I'm going to have minus x to the 3/2. And now we can integrate this. Right? X is just x squared over 2. X squared over 4 is just x to the 3rd over 12. And x to the 3/2 is 2/5 x to the 5/2. And we're going to evaluate from 0 to 4. The nice thing is when we plug in 0 to each of these, and make sure you always check this because it's not always true, but in this case, when I plug in 0, I just get 0. So really all I have to do is just evaluate each of those at 4 and find the answer. So 4 squared is 16. 16 over 2 is 8. And then we've got 4 cubed, which is 64 over 12. Right? So 64 over 12. Those can both be divisible by, or they're both divisible by 4. Right? So that's 16 over 3. So we've got 8 plus 16 thirds here. And then we've got 4 to the 2/5. Right? So first we'll square root the 4, right? That x to the 1/2 part is 2, and then 2 to the 5th is 32. So really what we've got there is 32 times 2/5, or minus 64 fifths. And it looks like a common denominator there is going to be 15ths. 8 times 15 is 120. And then 16 times 5 to make that one fifths is 90. And then 64 times 3 to make that one fifths. Right, 64 times 3 is 192. Is that right? 60? No. Yeah, 192. That's right. So we got 120 plus 5 times 16 is not 90. I try to do my arithmetic correctly. 5 times 16 is 80. That's kind of bad. So we got 200 minus 192, which is 8. And our denominator, as we said, a common denominator was 15th. So 8 over 15 as our final answer there for part B. And that was worth 3 points. 1 for the final answer, and then 1 for the correct integrand, and 1 for the correct antiderivative. All right, and in here on part C, we're just asked to write, not evaluate, an integral expression if we were to rotate this region around y equals 2. Right, so the first thing we'll note is if we're revolving around y equals 2, that region is not fully pushed up against that line we're revolving it around, which means there's a gap. Which means instead of just getting discs or circular cross sections, we get these washers, right? We get a circle with another circle cut out of the middle of it. And the radius of the outer circle is just going to extend from the region, the line we're revolving around, to the bottom of the region. And our inner radius is going to extend to the top of that region. Right? So this is going to be our inner radius. And this one is going to be our outer radius. Well, that distance is the entire distance of 2 units minus whatever the value of each of those functions are. So our outer radius is going to be 2 minus the lower function, which is x over 2. And our inner radius is going to be 2 minus the upper function, which is root x. And so the area of these cross sections, right, it's pi times the outer radius squared minus the inner radius squared integrated. So it's pi times the integral from 0 to 4, because that's still our limits, of our outer radius, 2 minus x over 2 squared, minus our inner radius of 2 minus root x squared dx. And thankfully, they don't ask us to do all the algebra and integration and arithmetic on this. That's the end of that one. You got 3 points, 1 for the limits and the constant, and 2 for the correct integrand. And that is the end of this area and volume FRQ, question number 4 from the 2009 Form B AP Calculus AB exam.